Let's start the last session this evening when Mariano Santander is going to teach us about Oscar abilities as a singer.
Well, yeah. Well, thank you very much. Well, it is really a pleasure for me to be here to celebrate this long and fruitful career of Oscar. I had the privilege of being at the beginning of this career, and it is, as Hans Bethe sometimes told, the best for any researcher is to see how his students start saying things that one no longer understands. So that has been the case with Oscar, of course, because he devoted mainly to more pure mathematics than I could think. And when I was invited to this meeting, as the title included something as geometric structures, I thought, well, what title could I propose inside this idea? And I thought that Newtonian gravitation is an interesting thing in that sense, because the geometric structure behind geometric Newtonian gravitation is not so well known. Well, this is the article we published with the Tesina of Oscar. In the beginning of the times, say in the pre-Higgs story, for as Oscar was concerned, and that was published in the Journal of Mathematical Physics, and it concerned a topic which at the moment was in some interest. Well, but after that, Oscar went to Rice, I think, and then Oscar continued his career. So I will pass to my talk. The starting point will be the last question. What if the idea of the connection had been defined around the beginning of the 20th century? Well, in actual history, this idea was proposed by Tullio Levi-Civita in 1917. This is important because this is after Einstein had created general relativity. The idea was put in a better form by Hermann Weyl and then by Elie Cartan, who generalized to the idea of an affine connection. And the main point in my talk is that probably this fact was some kind of an anomaly, because and this is what some historian of science has to say. Well, the idea is that everything was prepared at the beginning of the century to the idea of connection having been defined. But however, this had to wait some 20 years. And the idea is that this theory of affine connections allows a mathematically precise formulation of the Einstein insight that gravitation and inertia are essentially the same. And the absence of this context was a serious obstacle, indeed an unsurmountable one, to its development by the most direct mathematical route. Consequently, Einstein was forced to take some detour through a long and quite indirect route, and to this day, many discussions of the interpretation of the general theory still reflects the negative consequences of this detour. Well, so the idea, I have prepared the talk as a kind of uchronia. And uchronia is some narrative of how things could have been developed. not the actual historical development, but other way. And the most known uchrony is this novel, The Man in the High Castle, by Philip K. Dick, which departs from the point that Allies have lost the Second World War, and the states have been divided between Japan and the Germans. And it is quite interesting story, because inside this is another uchrony. So it is a quite of a very, very interesting structure. And the question is, well, but this why this is something interesting to physics or to science? Well, this here you have three quotations, and well, essentially all went to say the same. And the idea, I will read the Lévy-Leblond one. Understanding the unfolding of any specific stretch of history greatly benefits from imagining how it could have developed otherwise, if such and such crucial consequences have been different. So this is the spirit of my talk. Well, how history developed? Well, essentially these are the basic points. First, Newtonian gravitation, then electromagnetism, then Einstein, starting from electromagnetism, created special relativity, then Einstein, starting from nothing practically, created Einstein theory of gravitation, and after that, Levi-Civita introduced the idea of connection and parallel transport. And a few years later, Cartan showed that Newtonian gravitation can be seen as a geometric theory, which a kind of a connection and with a curved space-time. So the main idea is, well, can we try to imagine how things could have evolved if the idea of connection had been defined just before relativity? And as we will see, there are several surprises to be found in this story. Well, this is an outline. First, I will devote a quick glimpse to history as it was, speaking about Newtonian gravitation at the beginning of the 20th century, then about the development of special and general relativity, and then the creation by the geometric formulation of Newtonian gravitation by Cartan. And then the rest of the talk, I will put many elements in some structure which I will try to be as conceptually sound as possible, making this uchronia from Newtonian gravitation, say starting in 2 or 3 years before the beginning of the century. If time allows, I am practically sure that it will not. I will devote some time to speaking about the idea of a classical space-time, which is a quite more recent idea. Well, and again, quoting Lévy-Leblond, I completely agree with that idea. A presentation of science as it unfolded is not the only way to do it, and not even the best one. Alternative arguments and new derivations should be pursued and developed, not necessarily to replace, but at least to supplement the standard ones. So this is the main idea. Well, and this is all the dramatics person in this from Gauss, Riemann, and Christoffel by one side, of course, Newton, first and before, then Einstein, then Levi-Civita and Cartan, and then Schwarzschild, which, as we will see, have to play some special role in this reconstruction. Well, the first presentation will be the theme, which is how a Newtonian gravitation and inertial forces could have been described at the beginning of the 20th century. Well, the main idea is that the idea of an inertial frame, as we now has arisen just only 20 years before, and at this time it was clear that there was a big mystery, which is the fact that gravitational and inertial masses are completely equivalent and even equal in some sense. This is clear from the equations, because if we take the general equation of motion of a particle in a gravitational field and taking account of all possible inertial forces in the reference frame, well, the idea is that if we divide by the inertial mass, you get this, and only if this quotient is universally equal to 1, then the equation gets this form, and this turns out to be completely independent on any property of the particle or the falling particle. Well, so now we recognize that this independence is the most profound property of gravity. And that was done, clearly realized by Heinrich Hertz. He says essentially, well, I will not read the full quotation because this will be in the recording, but he says, well, this correspondence must mean much more than being just a miracle. We must clearly realize that the proportionality between mass and inertia must have a deeper explanation and cannot be considered as of little importance. So Hertz probably was the first to realize this clearly, because up to his time, this was considered as a happy accident. Well, now the idea is, can you separate and distinguish true gravity from inertia? Well, this is a long and interesting history, but the main result is that in Newton theory, rotation is absolute, and one can ask whether the linear inertia is also absolute or not. In fact, behind this is the full story of the Leibniz-Clark's correspondence, the experiment of the Newton, or the Gedanken experiment of the, no, not Gedanken, actually, of Newton's bucket, and the fact that inertia forces appear only when you are moving relatively to the rest of the universe, in the Mach sense. Mach, by the way, was later than Hertz. Well, the idea, you can see this clearly in the equations, because separate centrifugal and Coriolis effects is possible. This is the equation, and then, of course, if you launch a set of particles with the same initial positions but different initial velocities, this part will be the same for them in the accelerations. So the acceleration will differ by this term, and from this, of course, you can get the rotation tensor. But there is no any possible absolute separation of the true gravitational effects from inertial linear dragging. And this is clear again. This is the equation. And of course, one cannot say this part, this precise function of time is the inertial term, and this is the gravitational one, because of course, the important point is that this could depend on the position, but this do not. Well, so this idea, now you can realize that is essentially the Newtonian equivalence principle. And this is something which should hold universally in the case gravitational and inertial masses are the same. Well, let me make a quite fast exposition of relativity, just the minimum for understanding the following one. Special relativity describes space-time in the absence of gravity, and the Einstein theory of gravity describes space-time in presence of gravity. In both cases, the arena is some pseudo-Riemannian space with a Lorentzian metric with this signature that was first appearing in the literature by Grossman and Einstein in 1913. And the next ideas are the geodesic hypothesis, that free fall follows the geodesics of this metric, and the idea that the curvature is non-zero and is determined by the presence of energy and momentum, plus Einstein's equations, plus the differential Bianchi equations. Well, so essentially, this is the main point. Well, maybe one idea. Many people have said and defended that special relativity would have been likely proposed by any other author, not by Einstein, say sometime, some small short time later. Well, now I think that it is quite rewarding to consider three levels in Einstein theory: the metric tensor, the connection, Levi-Civita connection, and the Riemann curvature tensor. And the physics meaning of these elements are metric tensor describes at the same time, this is something rather mysterious, the chronogeometry of space-time and the gravitational potentials. The Levi-Civita connection describes the intensity of the ordinary gravitational field and the gravimagnetic field. And the Riemann curvature tensor describes the tidal force field, the tidal gravimagnetic field, and the three spatial curvature. Well, the idea that gravitation and inertia should be treated in the same way was clear by Einstein. And let me read this part. Can gravitation and inertia be identical? This question leads directly to the general theory of relativity. Is it not possible for me to regard the Earth as free from rotation if I conceive the centrifugal force which acts on all bodies at rest relatively to the Earth as being a real gravitational field or part of such a field? My conviction of the identity of inertial and gravitational masses aroused within me the feeling of absolute confidence in the correctness of this interpretation. So that was clear for Einstein. But the basic idea is, therefore, gravitational forces and inertial forces should be aspects of a single phenomenon and described by a single mathematical object. That was not available to Einstein, because he had the idea of a connection. Well, some few years after Einstein, Cartan gave an interpretation of Newtonian gravitation as a geometric theory. The starting point was about the possibility of formulating Newtonian gravitation in a fully covariant way. And this was, for Cartan, that was clear. There had been previously some remarks by Kreutzmann about the idea that the general covariant condition was physically empty, had no content. Einstein responded to that in a quite characteristic thing. Let me one express, well, after saying that essentially Kreutzmann was right, he said, let one express Newtonian mechanics four-dimensionally in the form of a generally covariant equations, and one will surely be convinced that the principle of relativity excludes this theory from the practical, though not the theoretical viewpoint. So Einstein was bright, of course, and probably he saw that essentially that was possible, but probably he had tried this because he says that this is quite complicated, and we will see that this is actually the idea. Well, what are the structures of the interpretation of Cartan of this geometry? Well, first, the chronogeometric structures in space-time, say temporal durations and spatial distances, should be described by two tensors. This tensor, it comes from a covector. Well, this should be closed, but I am not interested in this point here. This is related to the temporal durations and could be taken as a temporal metric. And this is a cometric because it is contravariant and is related to spatial distances. This should be satisfy some conditions, which essentially say that if you stay at rest, the simultaneous space for you is orthogonal in this matrix. And the important point is that these tensors are not dynamical. You see, these are the expressions in all space-time. So this is alike the case of Euclidean space in Cartesian coordinates, where the metric does not depend on the coordinates. Well, now the idea is that gravitational fields do not affect these structures. So when and where a gravitational field appears? Well, it appears through the inertial law and just by means of some connection. And this is clear. If you take the equations of a connection in four-dimensional space-time, take into account that the canonical parameter is the absolute time, is the length along the curves, which is path independent. And the question should be this: you compare this with the conventional equation in an inertial frame, and you get that this connection fulfills all the conditions. If you do the same in some non-inertial reference frame, this is the expression of the connection. Sorry, I am blocking you from the view. Well, I will. Well, this connection should be compatible in some sense that with the chronogeometric structures. And the main important point here is that this compatible connection is not unique. So this is different from the Einstein theory. There are two more important connections. They are called the inertial connection and the free fall connection. What is the difference? Inertial connection has as autoparallels only the inertial motions, but without taking into account the, say, gravitational field. And the free fall connection takes into account the possibility of an external gravitational field. So you see, these are different just by this term. Well, you can play all the standard play and take the curvature tensors of these two connections. The inertial connection is flat. The gravitational field can be considered as an external field, and the standard equations have this form, which is quite well known for everybody. In the case of the free fall connection, this has non-zero curvature, and the only elements in the Riemann tensor which are different from zero are these, which are in fact the gradients of the ordinary gravitational field. So this is the tidal field. In this theory, the free space is flat, and the equations of the gravitational fields involve the Ricci tensor, and the Ricci tensor automatically has only this component, say the time component. I am assuming I am using adapted coordinates, but of course you can reframe all this in a completely intrinsic way, independent of coordinates. Well, this quantity is just, sorry, and square is missing here. Well, so this is the Laplacian of the gravitational potential, and the equations of the gravitational field says that the time component of the Ricci tensor equals to the density of matter. Well, so to sum this, you can say that before Cartan, Newtonian gravitation had a single view, which was the conventional one, but after Cartan, there were two possible interpretations, both involving different connections. In one of them, the connection describes only the inertial forces, and the other, the single connection, describes inertia and gravitation. And that was the way chosen by Cartan and followed by Friedrichs, and then starting to be more and more explored, starting in the 60s. Well, so the idea is, well, there are two alternatives, but which one is preferable? The idea is that inertial connection is unobservable, and this is just a direct consequence of equivalence principle. So the Newton-Cartan, where there's just one connection, is better than that. And this is finding his way even in the textbooks at the moment. And this is just a quote by this work, and he says, well, after discussing that every honest teacher of theoretical physics is confronted at the very early stage of a classical mechanics course with this difficulty, then he says, well, a much more satisfactory formulation was given by Cartan and Friedrichs. This denies the separate existence of a flat affine connection of space-time and a vector field describing gravitation, but puts gravity on the side of a more general dynamical connection. So, and of course, they add, historically, this important step, of course, was made first by Einstein when he created his general theory, but is clearly independent of the relativization of the time. Well, so this is what we need from general relativity. And now I start the third part, which are the presentation of the uchronia. The idea is just to link several ideas in a way which is conceptually sound and without any, because I am not pretending that this could be a kind of historical reconstruction, because that was not, of course. Well, at the beginning of the 19th century, probably the best approach to be done was through a Lagrangian formulation. The inertial reference frame, this is the Lagrangian for gravitation, and if the frame is non-inertial, you should, it is quite simple. It is a simple exercise to compute the Lagrangian in the coordinates of the non-inertial frame. And this is the form, this is a gauge term, and this is the equations of motion. And the idea is that all forces here appear through a velocity-dependent potential, which includes, this is the, of course, the gradient of the potential, or minus the gradient of the potential, and this is the part which is velocity dependent. We can call this the gravitokinetic potential. And using this, the Lagrangian has this form, and you say, well, this is the same as the electromagnetic one. Well, not quite. That was done for the electromagnetism in 1903 by Schwarzschild. And it is quite, you can believe without any difficulty, that he could have tried the same for gravitation as soon as he tried to formulate within an inertial and non-inertial frame. how this gravitokinetic potential transforms when you change reference frame. Then the idea is the following. Well, you should assume that at this moment, the basic ideas of what is called now tensor calculus were known. That was true in some special circles, but if we assume that that was more known, you can clearly see that if you start use a four-dimensional Newtonian space-time, where the velocity has these components, then this Lagrangian is a quadratic form in the forward velocity, which have this form, and this gives you a quantity which should be a tensor 2 times covariant to ensure that L is an scalar. So the idea is that this tensor, which in fact encodes the potentials of the gravitational field plus inertia forces, this independently of whether the reference frame is inertial or not. Well, again, that was it is not quite difficult to think that that was available at the time. In fact, Schwarzschild, after his PhD thesis, defended in 1 year before than that, I think, who published some semi-popular book, and almost concluding that the idea of an inertial system has no an independent status, but is a partially conventional idea. And this forces one to take into account in the formulation of the theory. And you cannot say, well, let us assume that our system is inertial. That was a consequence of a previous work by his supervisor, Hugo von Seliger. But, well, this is simply to tell you that this could have happened at this time. How this gravitokinetic potential transforms? Well, this is the essential point. If this should be an scalar, this should transform as a tensor 2 times covariant. And if you write it in a rotating system, in a non-rotating system, or in a general rotating system, these are the expressions of this. And a question which is somewhat tricky is that the transformation law of potentials, the full set, cannot be linear, because otherwise, if in an inertial system the inertial potentials are 0, they will be 0 in another system. What is the point? Of course, the transformation for this tensor is linear, but this part is present here, and is independent of the coordinates, and makes that when you transform, there appear some new terms. So this is the main idea. It's curious that this point, this precise point, this is the oldest reference I have found in the literature by Louis Bell in the 1990s. So and the idea is that this kind of tensors, where the space components are these, preserve this condition under any rigid transformation. But in fact, the idea is that, well, this is a technical point. At this moment, a connection enters the stage. Well, what is the up to now? Everything could credibly have been thought in the moment. Now the uchronia starts, because you have to feign that the connection had been defined before that. And then the idea is that the way was prepared to describe the full set of gravitation and inertia in as a connection. Well, how could you do this? the autoparallels of the connection have this structure, and some bright people could, knowing both the mathematics, I mean the connection structure and so on, and physics, say the gravitation, could have thought, well, if you take this idea as the basic free fall equation, then Galileo principle gets explained, because this equation has no any reference to the mass or the inequality of the falling particle. Well, so what possibilities are there for this connection? Well, of course, as we have seen before, what Cartan did, it is clear that if you work, and this is not is rather direct and simple, you will find two connections: the purely inertial connection, describe only inertial forces, and the free fall connection, describing jointly both forces. Well, as the Newtonian equivalence principle implies that the purely inertial connection cannot be observed, you should choose this connection as the one describing the thing. So how is this connection? Well, compare the conventional equation, write it is in the form of a autoparallel of this connection, and play leading directly to this form of the connection in adapted coordinates. You say that all these elements are 0, and this is linked to the existence of the absolute time, and the elements of the connection with an upper space index, labeled by Latin letters, are these three. This is the ordinary gravitational field, and this is the inertial part. This is the Coriolis part, and this is the Euler and centrifugal part, and this is the linear dragging. Well, so up to this point, we could have a full idea about free fall follows the autoparallels of some connection. How to describe the chronogeometry? Well, again, this is the idea. It was already said by Cartan, but nothing prevents this to have been discovered before. Absolute time is this corresponds to this covector. This is the same in the form of a 2 times covariant tensor, which is the temporal metric tensor, and this is the equimetric, which describes the spatial distances. Well, and again, these tensors are not dynamic, because anything here describes the gravitation. So the idea is a gravitational field does not affect them, and ideal clocks measure temporal length if this is taken as a degenerate metric. Well, now we join the dots. The idea is, well, how are related these two different views? The view of free fall as a connection, and the view of free fall as a extremal of some variational principle with Lagrangian. And then, if you do a direct checking, we conclude that this is the connection, and you probably say, well, this is the standard expression of the Levi-Civita connection, but it is not, because these first kind Christoffels are taken from the tensor L, and the index is raised by the cometric of the space. So this is some different thing. Well, we make all the computations, and you find that this is the expression for this connection, and indeed this coincides with the one got through the variational principle. So everything fits. So from this point on, we have two different ways to understand this free fall. The three levels in this theory are rather more complicated than they were in general relativity, because in the first level there are the chronogeometric tensors, this Lagrangian tensor, which is different. From this and this we get some connection, and this connection is precisely the one involved in the Newton-Cartan theory. Well, so let's do the last step here. And the idea is, well, can you understand this free fall as geodesics of some metric? Well, so far we have seen that they are extremals of an axion and autoparallels of a connection, but no any metric appear here. Well, how could this metric, if it exists, could be? Well, of course, during the last third or half of the 19th century, there have been many attempts of starting different variational principles with minimum principles by Gauss, by Hertz, and by other people. So that was a quite natural idea. Well, how could you try this? The axion functional with this Lagrangian is an integral over the time. So probably you should look for a metric whose length along the curves is time. And the only candidate we already have is the absolute time tensor, but this cannot be play this role because the degeneracy of this tensor makes the length path independent, because this is the absolute time. And so you have to try something different. And then the physical idea that you could use, or could help you, is what is called the Einstein's shield argument. This argument is simply that if you emit light at some point and receive it at a higher point in some gravitational field, it would reach the upper point with a different frequency. And this is important. This is just a consequence of Newtonian equivalence principle. There are no any relativistic argument there. Well, so we can say, well, what could be the tensor which really measure the time as relate to the real frequencies of this, not relate to its propagation in space as special relativity standard approaching did. Well, and of course this idea was due in real history to Einstein starting in 1907. Well, what could be this? This is the simplest possibility. And the idea is that we have just two tensors, which are 2 times covariant. We have this T and you have this L. And there are quite much quantitative evidence in favor of absolute time. And this suggests that this new tensor cannot be quite different from this. So think as a kind of small correction and write this in this form, which is the simplest one. This is some combination. From the tensor point of view, this makes sense. This coefficient has to be a dimension inverse of square of velocity. It should be negative because otherwise there are problems with causality. So, and that means that this should be quite large in the standard anthropometric scale. And it is interesting that Maxwell also thought along some ideas similar to this. Not exactly this idea, but they also proposed this a constant like this, and he said this has to be a very large velocity and so on. But Maxwell had to stop because he was not able to thought of a material medium in which the energy of the gravitational field was negative. Well, now this is the our object. You see that these are the potentials, the part of the potential which includes gravitational potential and the potential of the inertial linear dragging. This is the potential which gives you the Coriolis forces. So this would be this new tensor. And the idea is, well, let us look and consider this as a metric and compute its connection. In that case, you get the first kind Christoffel symbols as the derivatives of n, and you raise the index with the same n, of course, and you make a series powers in 1 over c squared. And what you find? You find that the first leading terms is precisely the connection found in this naive approach, and there are other terms here which are in order 1 over c squared and higher. Well, so recovering all the Newtonian gravitation is quite clear from this approach. Of course, the important point is that this, if this is correct, the Newtonian free fall connection will not describe exactly the free fall. So this is suggesting that Newtonian gravitation is only an approximate theory, not an exact theory. But the temporal metric, the spatial cometric, and the Newtonian free fall connection all appear directly as the limit of this parameter going to infinity of the tensor n of the version contravariant tensor scaled by this constant and of the connection. So you see that this is suggesting you that you should go one step further than Newtonian gravitation. What is new in this tensor? Well, maybe this is somehow surprising the first time one finds it. This is the general form of this tensor when there are a gravitational field and inertial forces. And now we ask, what happens if there are no gravitational nor inertial forces? In that case, these two potentials are 0. You put 0 here, and what you find? This. And what is this? This is, of course, the standard metric of Minkowski space. So, of course, this is just in adapted coordinates. In terms of Minkowski space, you would say orthonormal coordinates, but you can describe, you can make all this in general coordinates. So this is quite curious, because somehow you have got special relativity starting from gravitation and without any reference to electromagnetism, which was the real way. So you have this scheme of the relation of the different levels in this Newtonian theory, which the Lagrangian tensor, of this new proto-relativistic theory, and the Einstein theory. Of course, this from the structural viewpoint, Einstein theory is the simplest, because there is just one metric, just one single connection, which is the Levi-Civita metric connection, and so on. Well, but you see that probably you should anyone have found or followed this line of thinking, probably the development of a relativistic theory of gravity could have been easier than it was. Well, and so the point is this theory a relativistic theory of gravity? And the point is, well, no. And why? Because this structure is clearly not compatible with special relativity, in the sense that space is straight in a completely different way to time. And if you say that special relativity makes that anything happening to time will have some other thing happening to space, and conversely, probably a relativistic theory should have at least this form with some quantities here, which would call some role of potentials, which possibly will depend on C. Of course, as soon as you consider this, you get some new expected effects, say gravimagnetism, spatial curvature, gravitational waves, which are not present at this level. Well, so I sum up. The idea is that as gravitation affects to the time necessarily, this Newton-Cartan-like theory must be modified, even with to prior knowledge of special relativity. And alternatively, this Newton-Cartan theory might even lead to special relativity. Well, of course, the lesson to be learned from this is that this theory would have made a new relativistic theory of gravitation much easier to build, because the connection idea was from the outset at this theory. Well, can you imagine that something similar have been actually done in these times? Well, of course, this is completely speculative, and all contrafactual affirmations are simply should remain in some special box. But of course, my view is that the people who was near to could have taken this point was Karl Schwarzschild. And if you can formulate the uchronia as such, you can say that this Karl A. Schwarzschild was the creator of this idea. Well, so what is the end of my message? Well, perhaps this uchronical reconstruction should be considered as unlikely. This is true, I consider, of course, but you should not consider, not forget, that real history was following a completely unlikely way. So maybe this is not more unlikely than this. And in any case, the idea is, well, understanding the unfolding of any specific stretch of history greatly benefits from imagining how it could have developed otherwise if such and such crucial circumstances had been different. So this has been the spirit of my talk. Well, so the idea is why things were much more complicated. Of course, if should this idea have been known before the time of Einstein, Einstein could have learned this probably through Grossman, and the full development of general theory of relativity would have been much less difficult and probably not prone to some misunderstanding which still remain in the interpretation of this theory. And the main point is that essentially the object which is really fundamental, both mathematically and physically, is the second level of our schemes, the connection. But Einstein was limited to work reducing everything to the first level, which was the metric. And in this translation, many things were quite complicated, including, for instance, the Newtonian limits. Well, so this quotation by Manning is very dear to me, and probably Oscar will agree. And essentially, it says, even those who see stars ask, what is a star? Because to see merely what one's eyes is still very little. The eyes of the mind must be able to see in the phase space of mechanics, in the space of elementary events of probability theory, in the cubed four-dimensional space of general relativity, in the complex infinite-dimensional projective space of quantum theory, and among other things, modern mathematics is a rigorous training in multidimensional perspective following a unified program. Well, so happy scientific 60s and maybe more years to come, Oscar. Thank you. I have prepared some slides about this, but probably this is the moment to stop.
Any comment?
Thank you, Mariano, for this fascinating imagining how things could have been in connections in relation to gravitation. There is another instance that I find very interesting also in the relation of physics and mathematics and involving connections, but in relation to particle physics. And this is the fact that mathematicians invented connections on vector bundles and principal bundles in the 40s, 50s, and the physicists like Young and Young-Mills were thinking of similar things and to describe particle physics. So do you think things could have been different? Not if things had been invented before, but if they had talked to each other, maybe, you know, like, or you can imagine a different path that would avoid, in particular, what you said that I like very much, this going to diverting routes that are always not so satisfactory.
Well, maybe I was too optimistic when I said, well, at 1903, some bright guy who knew the mathematics side of the connection recently defined and gravitation theory would provoke this merging of the fact is, in actual history of particle physics versus mathematical idea of connections as developed before Cartan by through Ehresmann and Kosul and so on, maybe the point was that there was no such bright guy knowing both sides. But anyhow, it remains as actually fascinating thing to see how things which were developed after some kind of diverging trajectories ended to be able to talk to each other and to describe a quite deep level of our understanding of both mathematics and physics. But I have not thought about this because, in fact, my involvement in all this has been mainly a consequence of I had to teach general relativity for many years, and I hated to transmit this kind of misunderstandings to the students. So I wanted to put things as more clearly defined and as possible. And in fact, I started this, say, 15 years ago, and along this time, there are a growing tendency on saying, well, you should teach Newton-Cartan gravity. This helps a lot to understand the things and so on. So
this could be the second part of your novel, right?
The accounts of the genesis of general relativity often present Hilbert as being just behind Einstein. How does Hilbert fit into your Uchronia?
Well, that's a quite good question. I am not so sure that you could the particular Hilbert contribution in this, because it depended, as I now, quite a lot of understanding the dynamics of some fields which were continuous, and probably before Emmy Noether's contribution, which she was at the moment that, and he was working on the idea of how differential Bianchi identities are involved in this. So Hilbert's contribution was based on a variational principle, but from a field in 4 dimensions, and which some Lagrangian, which is a rigid tensor, and so on. As far as I can imagine it, I don't see any reasonable way to fit in this part of the story. But probably the point that at the end of this story, Hilbert was involved, and he invited Einstein and was interested in the problem and so on, was somehow consequence of the difficulty of Einstein in getting the final field equations. So in fact, for instance, let me give just a data. It was not until 1915 that Einstein took the final decision to took the second kind Christoffel coefficients of a metric to replace the role of gravitational intensities of the field. So probably along this kind of route, this could have been quite easy. And but well, to go again to your question, I do not see any way to put Hilbert's contribution into this line.
May I comment on this? Well, this is quite surprising because, I mean, there was the work by Palatini, of course.
Yes.
As Palatini principle is important, it was clear that you can get the equation from a variational principle involving the Christoffel symbols.
Of course. What was 1920?
Yes, it was around, I guess that the first paper, it was 1918 or 19, yes.
Before the
Yes, before Cartan, yes.
Uh-huh.
So
Yes,
it was a work completely neglected in some sense.
Yes.
And it was very illuminating in this direction. That the main objects in general relativity
you are right. I have not well, I knew about Palatini formulation, but it was neglected
also because it is a bridge with Newton Cartan, because you can allow also torsion in the connection.
Even torsion.
Yes.
In fact, in Newtonian gravitation, you can also allow torsion, which is yes, that's an interesting point. I have not thought about
Maybe we can talk about that.
Yes. No, but the point is that Cartan was also quite neglected.
Yes.
Maybe he was a bit not considered by Einstein. I have the feeling.
Yes, because Einstein was, I think, unable to understand what Cartan. Cartan's papers are very difficult to read.
Yes.
In also the Cartan's style is quite difficult to digest.
Yeah, that's true.
There's a book of the correspondence between Cartan and Einstein that's wonderful, because the first thing is the remarkable efficiency of the postal system at the time. There are 2 letters going back and forth.
Yeah, that's true.
But the rest of it is they're like ships in the night. You know, they're just sort of.
So, in fact, there's relatively recently, there's a twistor version of Newton-Cartan geometry. In other words, you can describe it by, this is Penrose's twistor type theory. So this is Donaisky and one of his collaborators. He produced a geometry which is based on having a complex 3-manifold with a family of rational curves where the normal bundle is O plus O2. So what it's called self-dual geometry is O1 plus O1, but there's no self-duality here. It's O plus O2. So this is, holomorphic twistor theory version of Newton-Cartan geometry. I mean, it was a kind of curiosity, but I noticed there's a fairly recent paper by Donaisky and Penrose using it in some more physical context. So it's not dead. Let's put it that way.
Yeah, no. Of course, this is not dead. Even at the elementary basic level, this idea of classical space-time is still quite active. But probably at the beginning of the century, twistors could not anyway have been introduced. But it is quite interesting to.
Well, actually, that's not quite right. If you look at Penrose twistor theory, this is really, complex Klein correspondence. And so, but actually, I have a question for Nigel. What is the complex twistor space that they find? Oh. Okay. I see. Uh-huh. Okay. Yeah. Okay.
Well, you are beating me because we could try to include also Clifford.
Yes.
Because it was.
The first to understand the relation.
Yeah, that's true.
I think that we must thank again to the speaker.